All right, folks, let's do one more topic today. I'm going to move very quickly through this topic, which is arithmetic and geometric series. Yesterday, we took a look at the famous story of, I'm going to start picking names here. Hey, Ashani, how did Gauss add together the numbers 1 to 100 yesterday? He did the special thing with the other thing. Yeah. What's that? What did you say? Sorry, I missed what you said. Oh, okay, right. Yeah. 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 We see that pattern of adding first and last, and we put those together, and that's the average of taking any two terms. And then we can just use the idea of the average term and add that together with the number of terms. Right. And that works for arithmetic sequences, but not for geometric ones. We'll see we have a different formula for geometric sequences. So here are two formulas that we'll be using. Series do we have the definition here? Yeah, a sequence is a list of numbers. It's a progression of numbers that have a common difference or a common ratio. And those are either arithmetic or geometric. Arithmetic ones have a common difference that we find by subtraction. Geometric sequences have a common ratio, and we find those by division. Okay? And a series, well, this is a new idea, and that's when I take a sequence and add all the terms together. So let's take a look. If the sequence is arithmetic, we'll notice here that we have a lot of old friends, and they're showing up in a new way. N is the number of terms, so we write that there, and we write down series this way. The sum of a series and the number of terms there is equal to here. N is the number of terms. That's the total number of terms in the sequence. Okay. A is the first term. And D is the common difference. So those are old friends that we met yesterday. Wait, maybe they're new friends, and we met them yesterday. And this is the common difference here. Who wants to know where these formulas come from? Oh, that's too bad. I was going to shut you down by saying we don't have time. I don't have time to show you where these formulas come from. But in my opinion, this is the most beautiful thing that you'll see in this course is where the formula for a geometric series comes from. I'd love to be able to show it to you, but it would take me about 10 minutes to do it myself. And we don't have that kind of time or the attention span for it today. I know that we're in a tough spot. In a geometric series, this would be the sum of an n number of terms of a geometric sequence. The A is, again, the first term, FIR. So this is an FIRST term. R is the common ratio. And N, of course, is the number of terms. Here we don't have N minus 1, it's just N. And that's all divided by 1 minus R. Okay. We're going to use this formula tomorrow in a modified form for some really cool financial applications. Let's keep going. Okay, so let's take a look at this arithmetic sequence. If we were to write out the first 16 terms of this sequence and then add them all together, that's a little more challenging than the problem Gauss solved in like a few instants. But it's still something that we can totally conquer with the given formulas that we've got. So we're looking for a sum of an arithmetic sequence, and that's going to be equal to n over 2, the number of terms divided by 2 multiplied by 2 times the first term plus n minus 1 multiplied by the difference. And then we always go back and we verify our formulas. Oh, yes, Mr. Jennings, you wrote down the formula correctly. Congratulations. And then you pat yourself on the back. Say, yes, I remember the formula. Okay, so write it out each time you do some practice, and that's going to help you remember these. So S of n here, we want S of 16. And so I'm going to sub in here n over 2. Well, n is 16, so I have 16 divided by 2. and then multiply by 2 times a. Oh, here's a here. A. Okay, so 2 times 20 plus n minus 1, so that's 16 minus 1, so that's 15, multiplied by d. Well, what's d? Well, to find d, I can take t1 and t2, and I can subtract t2 from t1. So if I have 27 minus 20, that's going to give me 7. There's my common difference. D is equal to 7. And then I can verify 27 plus 7 is indeed 34. 34 plus 7 is indeed 41. Therefore, this is an arithmetic sequence, so I can use my mathematics for arithmetic series to add these together. So I'm going to multiply by d here, 7. Okay, and then I'm going to get S of the sum of the first 16 terms of this sequence is equal to 8 multiplied by 40 plus 15 times 7. 15 times 7 is 105. 40 plus 105 is 145. 15 times 7 is 105. Yeah, so this is equal to 8 multiplied by 145. And 8 times 145 is not that hard to do in your head. It is 1,200 minus 5 times 8, so it's 1,160. Let's just check on the calculator. I closed my calculator for some reason. 8 times 145 is equal to 1,160. So do it if you can in your head, and if not, and then if you're not confident, check your answer in the calculator. So this would be the sum of the first 16 terms of this sequence, 1,160. We could have just added them together and written out the first 16 terms, but that would have taken a lot longer than using this lovely formula. Let's keep going. In this situation, we have a Greek theater. There's 30 seats in the front row of the center section. So we want to imagine that we're standing in this Greek theater. We're looking up at the seats rising at some trigonometric ratio in front of us, and they open out by some angle so that each row has more seats in it. Like if I look at the number of seats in row 1, let's write it out. The number of seats in row 1 is 30. The number of seats in row 2 is 32 because each row gains an additional 2 seats. So there is my D. Okay, D equals 2. The next term would be 34, nice beautiful number, and then 36, very divisible number, and then 38, and so on, right? These would go on, and and we want to know, given that there's 13 rows, so that means n is equal to 13. There would be 13 rows in this theater, and we want to know the total number of seats. Okay, we can add this together like an arithmetic series. So we would have S of n is equal to a over 2 multiplied by, no, it's not a over 2, Mr. Jennings, it's n over 2. N over 2 multiplied by 2a plus n minus 1 times d. All right, let's sub in. S of 13, n is 13. 13 is equal to 13 divided by 2. Isn't this going to give us half of a seat? Isn't that strange? No, it's not strange. You'll see it cancels out. 30 times 2a, so that's 2 times 30, because our first term there, a, is 30, plus n minus 1, so 13 minus 1 is 12. I'm just going to write down 12. I'm not going to write down 13 minus 1. I'm lazy. And then d is 2. Okay. Now, evaluate. So I notice, actually, I'm multiplying by 2 all the way inside that bracket. I could cancel that 2 right there, but I'm not going to. Okay. This is 13 over 2. No way to simplify that. Multiplied by 60 plus this is 24. So that's 84 in the bracket there. 84 divided by 2 is 42. So I'm going to have 42 times 13. 13, Fibonacci, times 42. Life, the universe, and everything. Also, my age. S of 13 is equal to 13 times 42. 13 times 42 is, again, not that hard to do in your head, but ain't nobody got time for that. We're going to go in here. 13 times 42 is equal to 546. There's 546 seats. Now ask yourself, does that sound reasonable? 546 seats in this Greek theater. Yeah, sounds reasonable. It's totally reasonable that they would have that many seats. What about for geometric sequences? Here, let's take a look at this series here. Well, I want to first analyze it and find my A, my R. A is the first term. That is 3. R, I find that by dividing two different terms. So 6 divided by 3 equals 2. Or I could have used other terms. 12 divided by 6 also equals 2. And 24 divided by 12 is, you get the idea, this is a geometric sequence. Okay? And I want to add the first 12 terms together. So let's apply the math of geometric sequence. Geometric sequence, the formula looks like this. S of n is equal to the first term, A, multiplied by 1 plus r raised to the n, all divided by 1 minus r to the n. No, it's not 1 plus. Mr. Jennings. 1 minus r to the n, all divided by 1 minus r. And then I go and I check my formula and I make sure I got it right. I know I got it right, but there it is. A times 1 minus r to the n over 1 minus r. Congratulations, you got it right. Now you sub in and plug and chug. A lot of plug and chug this unit. A is 3, so I'll put in 3 for A. 1 minus r. R is 2. 2 raised to the power, we have 12. So this is S of 12, the first 12 terms of this geometric sequence. 2 to the 12. Isn't that going to give us a very large negative number? Yeah. But I'm going to divide by another negative number, 1 minus 2. So that's going to cancel out the negative and make it positive. And that's what we expect to find here is a positive answer. So, hurrah! Okay, let's take a look. We get 3 multiplied by, well, what's 2 to the 12? Well, 2 to the 12 is, you can watch me do it on my fingers, or you can do it this way. So I'm just going to type in what I've got over there. So I'm going to have here, clear everything. 3 multiplied by bracket 1 minus 2 raised to the power 12, end bracket. So that's what's inside the bracket there, all divided by, and that's what I have when I multiply by 3 on top. So that's what's on top of this fraction, negative 12,285. I'm dividing by 1 minus 2. 1 minus 2 is negative 1. Divide by 1, make it a negative 1. It's just going to flip the sign, and then this is my answer, 12,285. 12,285. Okay, so that's the sum of the first 12 terms of this sequence here. You'll also notice that the last few terms are contributing a lot, doing a lot of the heavy lifting to get that number that high, because they're the biggest, and they're bigger by big factors. They're bigger, they're twice as big as any previous term by definition, because our ratio is 2. So we can have these show up in your life and with money. For example, in this situation, Derek, he's earning a $35,000 salary, but only in the first year of his career. So there's A. A is 35. So I'm going to write out the sequence here. It's going to look like 35K. K means 1,000. That's the first term. The next year, he gets a 3% raise. And every year after that, he gets a 3% raise that's added to itself. So it's going to create a geometric sequence or an exponential curve. Okay. And we want to know how much does he earn in his 25 years of his career. So the next term is going to be 35K. It's going to be that A multiplied by the ratio once. And so that would be 1.03. And the next term would be 35K multiplied by 1.03 twice. So I'm going to raise that to the power 2. And so on and so on and so on until big money he's making in his last year, 35K multiplied by 1.03 raised to the power 25 minus 1. Why 25 minus 1? He didn't get the raise in his first year. That's his first year of earnings, is to the 0, right? And then to the 1 is here in his second year. So that's why this is 25 minus 1. Let's just, for fun, see how much he earns in that last year. Getting this 3% raise. So I have $35,000 multiplied by 1.03 raised to the power 24 equals, so in his last year, he's making $71,000. He's almost doubled his income over 25 years, which is, that's a pretty good rate of increase to his earnings, right? Over 25 years, he's earning double. Cool. Now that's a sequence. The amount he earns in each year is a sequence, and it's growing geometrically. So we can use the mathematics of geometric series to answer this type of question. Write out the formula. S of n is equal to the first term multiplied by 1 minus r to the n, all divided by 1 minus r. And here we have r is 1.03. So let's put this in. A is equal to 35,000. I'm just going to write down 35. And I'll know to add 3 decimal places. Sorry, move the decimal place 3 times when I check my answer. 1 minus 1.03 raised to the power n, which is 25. N, not n minus 1. So this was just calculating how much he makes in the last year. But when I use this, it says raise it to the power n, please, not to the power n minus 1. Okay, good. I will do that. And then here, this is all over 1 minus 1.03. Shawnee?
So when you have the negative 1 and the 25 there, and it's because of the first one, but when would you start putting negative 1?
Where? The 25? Oh, 25 minus 1?
Yeah.
Oh, this was to find how much money he makes in his last year.
Okay.
So that's when I'm looking at a geometric sequence. If I look at the formula for a geometric sequence to find the general term is equal to the first term multiplied by the ratio raised to the power n minus 1. That's my general term. So for the nth term, which is the 25th year, I would have 25 minus 1. Now that's like me going back to a formula. When I built that, I was just working intuitively. I knew that in the first year it was to a 0, so I knew that I was subtracting 1 from the year and to find the exponent.
This is kind of the same thing, but why don't you do that on
Here?
the second one?
In this formula?
Or no. You said
S of n?
minus 1, go off one line. No, I mean like where it says 35K, that
Yeah.
sequence there. Why didn't you do it on the third number?
Oh, I could, if you want, I can. This is the first term, right? So this is 1.03 raised to the power 1 minus 1. I'm 42 times 1.03 raised to the power 1 minus 1.
You just didn't write it.
I just don't write it because it's 1. Yeah. And then this is 1.03 to the 2 minus 1. This is 1.03 to the 3 minus 1. So it is there, but I just didn't write it. Yeah. I built this intuitively, like I was saying. In his second year, he will get the raise once. In the third year, he will get the raise on top of the raise. And so on and so on and so on until in the last year, he will have received the raise 24 times. Okay? And then with the formula here for the sum of the sequence, which is a series, notice that it's just n. It's not n minus 1. So don't make that mistake. Okay? It's to the n. And that has to do with the way we derive the formula here. And I don't have time to show you that because it's way too cool and you have to read your textbook if you want that level of coolness. So this I can punch on the calculator. So let's do that. Let's move it over here. We can punch on calculator and we say 35,000. I'll put in the 1,000 here. Sure, no problem. Easy to do. Multiplied by 1, brackets 1 minus 1.03 raised to the power 25. End the bracket and divide the whole thing by 1 minus, I'll do it for you, 1 minus 1.03. Notice I could have just done negative 0.03, and that would have also been the same thing. Equals, what? I forgot some brackets. Ha ha ha. Do the whole thing again, Mr. Jennings. Ha ha ha. Forgot some brackets. When you're punching into your calculator, don't forget these brackets. Also, notice that I knew that answer was wrong right away. It's important to have a good guesstimate for what your answer is and not trust your calculator. You have to trust your math. Multiplied by bracket, 1 minus 1.03 raised to the power 25. End the bracket. Divide by another bracket. 1 minus 1.03. End the bracket. Equals, there is how much money he will earn over his 25-year career. $1,276,074. 25 cents, so he can make a phone call and buy a nice house these days. So that's a 1276. I'm going to use that. 1,276, 0. I think it was 74 and 25 cents. There. So therefore, he earns $1,200,000 over his career. Cool. There you go. That's how you use geometric and arithmetic sequences. Okay, so take a look at the delta math for this one. Delta math 6.2. Yes, I flipped the order here. The reason I flipped the order is you'll recognize that these create sequences as you look at how much money there is in those different investments over time. Simple interest creates arithmetic sequences. Compound interest creates geometric sequences. Now we're looking at series, adding those together. So you bet tomorrow we're going to be doing that with money. Because that's our last topic for the whole class is tomorrow. All right. Any other questions before we wrap this up? Adding together sequences of numbers is called a series. Any questions? Use the formulas, practice the formulas with Delta Math. Delta Math gives you instant feedback. And find me with any questions.